Welcome to the Foundry by Forge College. Okay, let's be real for a second. We are finally upgrading from the sheer panic of manual deployments, the kind that inevitably ruin your Friday afternoons, and moving into the beautiful world of fully automated, self-healing deployment scripts. If you caught our previous explainer on structuring deployment scripts, we laid down the modules: configure, build, publish, and verify. But having a good structure alone doesn't actually save you time or stop human error, right? Today, we're taking those neatly organized steps and binding them together into a single, unstoppable, executable script. Now, you might be wondering, why go through the hassle of writing code just to deploy code? Honestly, because human error is inevitable. When you're manually copy-pasting file paths and squinting at messy terminal outputs, things are gonna go wrong. Maybe you forget to check if the build succeeded before publishing, or oops, you accidentally deploy the same outdated file twice. What we really want is a reliable, tireless machine doing all the mundane checks for us. That way, we can actually sleep peacefully at night knowing our pipeline isn't relying on our own fragile memories. So, here is the engineering schematic we're tackling today to build our automated solution. We'll start with the 3 pillars of automation: blueprinting our environment, actually build the engine, tackle the item publish phase, set up our verification checkpoint, and wrap up with some next steps. Let's just dive right in. Kicking things off with part 1, the 3 pillars of automation. To build a truly robust pipeline, our script needs 3 fundamental superpowers. These aren't just nice-to-haves. They are the absolute bedrock of any professional DevOps workflow. All right, let's talk about a slightly intimidating word: idempotence. It's a massive concept in computer science. Think of it like a highly intelligent copy machine. If you hand it a document and say, "Hey, copy this," it makes a copy. But if you accidentally mash that copy button 5 more times, well, a dumb machine spits out a mountain of wasteful duplicates. An idempotent machine, though, it realizes the exact output already exists, politely ignores your frantic button mashing, and leaves you with just that one perfect copy. In our pipeline, this means accidental double triggers will never break the system or create duplicate deployments. So, alongside idempotence for safe repetition, we need retries. The internet is a wildly unpredictable place, and sometimes network requests just randomly drop. Retries give our script the persistence to try a flaky task a few more times before completely throwing in the towel. And finally, verification. Because we want to mathematically prove our file arrived safely instead of just, crossing our fingers and hoping for the best. By the way, as you explore other Web3 courses at Forge College, you'll see these exact same 3 pillars popping up everywhere. They really are universal. Moving right along to section 2, blueprinting the environment. Before we write the core logic, we absolutely have to wire up our environment variables. We never ever want to hard code specific file paths or sensitive secrets directly into our code. Think of these variables as the control dials of our machine. Our build command dictates how we create the file. The artifact path tells the script exactly where to find it, the deploy directory is our destination, and our retry count is our persistence dial. By using something like .env or standard shell exports, we can swap these dials out on the fly. You could run the exact same script locally on your laptop with dummy paths, or in a secure cloud pipeline with production paths, completely seamlessly, without touching a single line of your actual logic. Now for part 3, building the engine itself. Let's pop the hood and look at the mechanical steps of our Node.js deploy script. How do we actually string this all together to get the work done? The flow here perfectly mirrors a logical human workflow, just infinitely faster. Step 1, we run the build task using a synchronous shell command. Step 2, we publish the artifact, which for our local learning script today just means safely copying it to a version deployments folder. And step 3, we mathematically verify that it arrived without a single corrupted byte. But here's a really clever trick. We wrap all of this in custom retry logic right at the task level, using a little helper function called run with retries. If a network blinks or a file is temporarily locked during one specific step, our script just retries that tiny step up to our limit. It is vastly safer to retry a single failing upload step than to stubbornly restart the entire deployment script from scratch and accidentally cause a massive mess of unintended side effects. Let's jump to section 4, the idempotent publish. Let's see how we actually build out that crucial first pillar. How do we make the script smart enough to know a file is already sitting there? This secret weapon here is a technique called content addressing. We don't just copy our program file to a new folder and keep its boring old name. Instead, we read the contents of the built file, generate a unique SHA-256 fingerprint of its data, and use that fingerprint as the new file name, so it becomes artifact-checksum.bin. If the script checks the destination folder and sees that exact fingerprint name already sitting there, it knows with absolute certainty that this exact version is already published. It just skips the copy entirely. Literally zero wasted effort.
Now, a raw binary file isn't quite enough for a healthy pipeline. So alongside the binary, we generate a small JSON metadata file. This tracks the exact timestamp, the original source path, and that specific checksum hash. This is huge because 6 months from now, when someone on your team asks, wait, exactly when did we deploy the specific version? You aren't guessing. You have a built-in, unarguable audit trail right there on your machine.
On to Section 5, the verification checkpoint. Because hey, trusting the process is nice and all, but mathematical verification is a whole lot better. So, how do we prove no data was corrupted while copying over a network or moving across a hard drive? It's simple. We recompute the fingerprint on the newly deployed file in the target directory, and we strictly compare it against the original source fingerprint. If those two strings of text match exactly, we have absolute mathematical certainty that zero corruption happened. If they don't match, the script throws a hard error, basically acting as a bouncer to prevent corrupted code from ever going live. Invisibility is totally key here. When you run this machine, you do not want a silent success. Your terminal should light up like a diagnostic dashboard showing all the signs of a healthy launch. You want to see an exit status of 0, which means no errors. You want a clear, time-stamped success message, and both your 64-character hex file and metadata file sitting safely in the folder. If anything fails permanently, these structured logs isolate the exact problem instantly.
And here's the ultimate test. If you run the script immediately a second time without changing any code at all, you should see a log message saying, artifact already published, skipping copy. That little message right there, that is your golden proof. It means your engine saw the work was already done, verified it, and gracefully stepped aside without causing any redundant side effects.
Finally, Section 6, next steps. If you've been following along and building this, massive congratulations. You have just built a local, self-healing deployment script based on incredibly solid professional engineering principles. It's safe, it's repeatable, and it actually verifies its own work. But of course, local file copying is just the training ground. In our next explainer on scripted workflows, we're going to take this exact script and transition from moving files locally on a hard drive to executing real Web3 program publishing. We'll even perform query-based verification directly on the blockchain. Because we built this using environment variables and structured logs, this script is practically begging to be dropped right into a production continuous integration pipeline. If you want to master these cloud integrations, evolve your local scripts, and dive much deeper into Web3 engineering, make sure to visit forge.college to continue your learning journey. But before you go, honestly ask yourself, how many critical deployments in your current projects are still secretly relying on someone remembering to press the right buttons in the right order? Keep experimenting, have fun building, and I'll catch you in the next explainer.